All right, shall we begin? Everyone is here. Hello, everyone. Thanks for having me. My name is Sanjar. I'm a data scientist at Alif. I've been doing machine learning stuff for more than 4 years, I guess. I have some experience working with deep learning, and I guess I am fluent enough to talk about one of the main technologies of recent years called transformers, or transformer-based neural networks. As you can see in this slide, the transformer is some of the essential parts behind such innovations as Lambda, ChatGPT, DALL-E, and I'm sure every one of you have already used maybe or heard about it. So let's begin. First things first, let's talk about how it all began. The very first version of Transformer looked something like this. Let's think for a moment about Google Translate. You have a space where you can enter your text, say in English, and another space which gives you to suggest your translation, say in Russian. English here is your source language, Russian is your target language. Similarly here, we have encoder model, something that we call encoder part of the transformer, and the decoder part of the transformer. Encoder learns from your source language, like English, and the decoder from the target language, respectively. What's interesting here, encoder learns the representations of your text in English state, and then passes as this hidden state for the decoder part in Russian. So the decoder part learns its language itself, but also receives the representations from the encoder in order to make its translation more fluent. This design pattern, I would say, was known before transformers, but one thing that was really monumental is the way how this model learned contextual representations of the languages. We will talk about this in a little bit later in more detail, but let's see some of the numbers of the transformer and why it was created. As you can see here, from 65 million to 213 million parameters, this transformer offered. 65 million is a rough number, and this is about the very base version of the transformer, and 200 million parameters was the large version of the transformer. And the main task that it was designed for, machine translation, from English to German and from English to French. But what's also interesting to note here, the researchers suggested using only the encoder part of this transformer in order to solve your downstream tasks. Say you have a marketplace, your customers write comments about your goods, and you want to understand if these comments are positive or negative. If you have really thousands of texts, there's no point in having a person that would check all of these texts and mark as positive or negative or something. So now more details about transformers. As I noted before, you can the authors of the original transformer said that you can actually use only the encoder part in your own tasks. Another Google scientists noted that pre-training only the encoder part makes sense in order to understand your source languages. In this example, say there's a text in your corpora, like I love deep learning. If you had machine translation task, your target would be "Я люблю глубинное обучение" in Russian. But when you don't have targets, how can you learn the language? How can you make your neural network understand your source language? Here's the suggestion. Take your text, your sentence, and randomly replace one of these words to the special token called mask. And then make your transformer predict this task and learn from its mistake. Say, we have here, I something, this red car. What should go in the place of mask? Say, I sleep, this red car. No. I love this red car. Something, matches the semantics of the English language. So this is something we call masked language modeling. If you pre-train your encoder transformer in a text, in an encyclopedia or some big corpora, you can strive for having a neural network model that knows the language even something more than a human itself. Another thing to note here is this part, which we call attention. The original transformer was, the title of the original paper was "Attention is all you need." I'm sure some of you here know already about what recurrent networks are, what convolutional networks are. These were one of the main tools in order to model languages. But the authors of the original paper offer that you don't really need no convolutions, no recurrent layers or anything like that. Only attention. And the attention part is something that helps your model to learn contextual representation of your words. What do I mean by contextual representation? We don't want to learn just the meaning of word I. We want to understand how this word I relates to other words, like to the word love or to the word car. And I'm sure you will all agree that this word should pay more attention to the word love than maybe to the word car. Is that the case? Similarly, if we model the word red, it should pay more attention to the car than to the word I. And similarly. So the design of these transformers automatically learn these contextual representations. Okay, now we have a pre-trained transformer. We hypothesize that it understands our source language, but how can we prove it? There is a way to prove this with fine-tuning. Fine-tuning means applying your pre-trained model to your downstream tasks. Say in our example with marketplaces, with your comments, if the number of text that our transformer learned was like, I don't know, millions or even billions, the whole internet, maybe your downstream tasks are much smaller, like thousands of comments maybe. And there's no point of training a new transformer for you or new recurrent network really. You can fine-tune your model using the previously trained or pre-trained encoder-only transformers. Here we have something that we call global representation or CLS special token. CLS summarizes your text. We can say very briefly, here we have the text, this show is not bad. It's about ratings, yeah? And CLS summarizes these words in one numerical representation. And then you add here your custom layers, say linear layer or something else, and try to adapt this transformer to your own tasks. Okay, what about numbers? Despite this transformer has only the encoder part, its numbers were up to 350 million parameters, larger than the encoder and decoder original transformer. Also, if you think that you can use this transformer only for text, you're wrong. Because if you have structural data, it really doesn't matter if it's text or something else, say images. You can similarly apply masked language modeling, no pun intended, masked language modeling to your images. Just in a similar fashion, make your images like tokens or what we call patches, and you will get a vision transformer, which was introduced into 2021. And you can use this for your downstream image classification task, for example. Okay, Was the encoder-only transformer the only option? Of course not. If we have a decoder part, it can exist for itself. The only thing that we should get rid of is this cross-attention. I mentioned that the encoder summarizes its representation, then passes to the decoder. If we translate some big sentences from English to Russian, we sometimes don't really need some of the words for our translation. Maybe articles like a and the, which don't exist in Russian. Here comes the attention part, valuable. But since we no longer have the encoder, we don't really need this cross attention. Moreover, decoder was used to generate new texts. If you generate new text from the current tokens, like here, I like, you can't, if you're in the word like, you can't just look for the future and attend these words. Therefore, we have something that we call autoaggressive language modeling. If previously we used masculine language modeling, in which our encoder was bidirectional, the word, say, I love deep learning, we had text, I love deep learning, the word love could attend toward learning, toward deep, and toward I. But in this example, I love deep learning, if we have generated the word love, we can't look for the future, right? We don't know the word deep or learning, we haven't ever generated it yet. Therefore, we get something that we call autoaggressive language modeling. It might seem for you that this model is somewhat restricted, but what is ridiculous is that modern day transformers that you all know, like ChatGPT, they are all decoder-only transformers. They actually generate text in a unidirectional pattern or autoaggressive pattern, and they seem to be the largest ones. The first GPT, I don't really remember how many parameters are, like maybe hundreds of millions, but the GPT-3, which was introduced in 2020, had something about 170 billion parameters. Really, you can't like get your laptop and install or, I don't know, download and try to use with Hugging Face or anything like 170 billion parameters. It really learned, I guess, the whole internet. Another examples of such decoder-only transformers are Megatron by Microsoft, if I'm not mistaken. Again, 530 billion parameters, ridiculous. And can you apply these transformers to your own task? You actually do. When you say to your GitHub Copilot to generate your code based on your documentation, this is actually you're using the GPT-3 by OpenAI. GitHub Copilot is based on the model called Codex, and Codex is based on GPT-3, and it's a decoder-only transformer. And another thing that to note here is that you don't really have to update the parameters of this decoder. You can pass you can do something that we call in-context learning. You pass your task, say summarize the following text, and it gives you the prompt, the summarization of your text. Something that we note here as a zero-shot learning when you provide no examples at all. Just say translate me from this text from English to French. One-shot learning when you provide only one example, and few-shot learning when you provide several examples. Again, we are not restricting ourselves here to just use texts. We actually at our math institution trained our own GPT on molecules. We had tens of millions of molecules and learned our GPT model to generate new molecules and also to classify some of the molecular compounds, like if it's active towards some disease or not. All right. So the third model, the third architecture that I want to talk about is encoder-decoder, which is kind of the same architecture as the original transformer, but the objective changes here. It resembles somehow the objective of masked language modeling, but the difference here is that you mask also randomly for the encoder, but for the decoder you mask your tokens in reverse order and have the special token called Z, or sometimes they call EOS, which represents the end of the text. Again, this is a ridiculously large language model which has billions of parameters, and one of the examples here is T5 from again Google researchers. We're not biased towards Google, don't really think this way, it's just an example. There are actually so many transformers here which are not necessarily trained by the big tech companies. Here's the example of fine-tuning of the encoder-decoder, which is kind of similar to what you do with the decoder-only transformer. You have your task and you have your prompt. And the encoder learns everything in a unit bidirectional pattern, and the decoder in an autoaggressive pattern generates the summary that you have prompted here. I can see that there were so many technical details. Let's review our lecture with more illustrations, I guess. These images were generated by the model that we all know as Imogen. Imogen, DALI, maybe you've heard about these models. They are also based on the transformer models. Of course, they use some additional tools like diffusion models, but the core thing to understand the text is transformer. In the case of Imogen, it's T5. In the case of DALI, it's GPT-3. Also, there are transformers which resemble, artificial general intelligence, like Gato. Gato was advertised to be the large language model with billions of parameters and knowing how to solve more than 600 tasks, like doing, generating texts, classifying your text, like playing Atari with you. This is ridiculous. And the last thing to note, you all know, you have already heard and used about ChatGPT, GitHub Copilot, and many others. They are all based on GPT-3. And all of them are transformers, actually. So the last question I want to address is that what is the future of these models? Can we think of any endpoint of these transformers? It seems like you train them more, you add more and more parameters, you add more and more tokens, and they're learning better. Is there any checkpoint that we have? It seems that we are not, because it is empirically shown that transformers can scale following the power law. If you're from computer science background, you know this. Also, there's something that we call inductive bias in machine learning. Every machine learning model has inductive bias. Say linear regression. There are so many assumptions when you use linear regression, but one of these assumptions are that the target that you want to predict and the futures that you have linear relationships. If this is not the case, it doesn't matter if you have billions of texts or anything. If this is not the case, your model won't work. This is inductive bias, one of the inductive biases of linear regression. But it seems like the inductive bias of transformers is almost unknown. It has no restrictions at all. It's just attention layers first, then something that we have positional encoders and etc. This is something technical that I don't decide to cover. But the thing that inductive bias of transformer seems to be unrestricted. Therefore, you feed more data to the transformer, it learns better every time. So this seems to be the reason why transformers are growing, why we have these big number of parameters, and why modern day big tech companies are competing with each other this way. I guess this was everything that I wanted to cover. The sources of these images and some of the slides are the book Dive into Deep Learning, if you want to learn more about it. So I'm ready for your questions. I hope it was insightful for you. Thank you.
If you compare, for example, transformers and autoencoders, they both have encoder-decoder architecture. Can you explain a bit more differences between them? About this attention.
You know, from the knowledge that I have about autoencoders, we don't really have anything that is related to attention in autoencoders. We have like two models. Say, as an example, if the encoder part is like recurrent network, we get the hidden representation and pass it to the decoder network. As the design pattern, it might seem similar, but there's no attention between encoder and decoder. This might be the key difference between autoencoders and the original transformer architecture. But I'm not really sure, because I have used autoencoders with the current networks. There was no attention at all. It was a variation autoencoder with noise added between these two, blocks. But I can see that you may actually use instead of recurrent networks transformers as well. So this is rather similarity, not the difference. But this is my suggestion, but I don't really know about it. Okay.
So how we measure the accuracy of the models? For example, front-end and back-end developers write unit, integration, and some kind of tests. They measure according to the test cases. And for example, in terms of models, how they measure?
There are several things that we call benchmarks. Benchmarks are the data sets plus the latest results related to these data sets. Like, I don't really think that the names will have any insights for you, like glue, superglue. Have you heard about? Okay, these are the data sets with labeled data that we try to learn and test. For example, you have a labeled data available for open source, which is about, again, reviews, yes, comments. Then you may first pre-train your transformer, get this data, fine-tune your transformer to adapt to this data, and measure, as you have said, accuracy or many other metrics related to the classification task. So this is one of the ways to measure. Another task may be matching two texts. Like the first text is a question, the second text is similar or dissimilar question. There are many benchmarks really available in English. I'm not really sure if they're available in Uzbek really. So this is the way. You're not just saying that, hey, I have trained my own transformer and it seems to be working. No, you have sets of data sets, usually several, which are related to many different domains, like maybe science, say to the internet, or I don't know, to social media. There's so many of them, and you fine tune or use transfer learning of your transformer to these tasks, and report your, as you said, accuracy or other metrics. This is the way to measure transformers, and actually all of them were measured this way, because no one accepts your big, best model if you don't provide these benchmarks.
Okay. Thank you.
I have a question. You mentioned about the method of learning. When you was talking about texts, you have said that there was pre-training, the encoder with mask data. And then you have mentioned about ViT models, and there is a method of pre-training also some imaging transformers with some masked. You mean you just drop some pixels from the image?
Not necessarily pixels. You may drop patches of your data. Not just pixels, because if we measure everything by pixels, I mean, what was the size of the sample in ImageNet. I think 224 to
Yeah.
something
Yeah.
that.
Yeah.
And you have, you know, thousands of pixels. You don't really want to like mask only pixels. You may patch, you may mask patches of your images actually, and learn this way.
Mhm.
Any other questions? Yes, please.
Yeah. We may know transformers for like several years, and they are doing really good job. And we are coming to the question of like explainability, like how, why it's giving what it's giving, like in the ViT or something others. Like, how are you seeing the road to that one? Because like in particularly medical imaging, like you have to show why you are giving these results, or some kind of other applications such as BART or Bing, GPT, like the misinformation comes in. So how are you seeing the road towards explainability?
Okay, I want to mention that the attention part of all of these models is something that we can relate to interpretability. I don't really provide here this the screenshots here, but I guess it was kind of a mistake. But you know, these attention patterns that you have here can be related to the interpretability that you're saying. Say if this word "I" attends only several tokens, you may interpret this word as being important only in this context, but not other contexts. With the image, again, you have your patches of images, and the attention pattern here helps you to visualize what areas of your image this particular patch attends to most. This is one way to interpret your transformers, but if you're talking about interpreting, you know, the features that we have, or explaining to your medical professional why does this works, it might be tricky. I'm not really, you know, expert on interpreting transformer models. Maybe there are some techniques that I'm not really aware of, but the attention part here is for explaining, you know, why we succeeded in this particular case. With recurrent networks, it was kind of difficult to do this because of their hidden representations and etc. But with attention, it's much better. I hope, you know, I have to some extent covered your question. Okay.
And you haven't told us